It is my pleasure to welcome our speaker today, Mads Holm Christiansen from the Costerton Biofilm Center, University of Copenhagen, Rigshospitalet. We are very, very happy to have you here. You've been using the calScreener for a long time. You're kind of doing the real experiments with it. And today I feel like we're just going to really get a good deep dive into what you're doing, into an application, a subject that is extremely close to our heart at SimCell. So without further ado, Mads, I'd like to hand the floor over to you. Thank you very much.
Thank you very much for having me. Yeah, I'm Matt, and I'm doing a PhD at the Costerton Biofilm Center at the University of Copenhagen, and also partly at the Copenhagen University Hospital connected to the university. And I'll be talking a bit about my PhD project so far, what I'm doing, which is, as you can see from the title slide, trying to expedite the diagnostic process of osteomyelitis infections using isothermal microcalorimetry. Towards the end of my presentation, I'll just touch upon some extra topics that I find interesting and what you can use this microcalorimetric data for. So just briefly about the type of infection that we're looking at, which is osteomyelitis, an infection that's expected to increase in the coming many years, partly due to the many comorbidities to this infection, such as diabetes and poor vascular circulation. And also we see an increasing rate of prosthetic joint infection and arthroplasty surgeries. So this type of infection is expected to increase. It's a very heterogeneous disease, and it can occur almost anywhere in the skeletal system, as you can see on the figure, and it can be caused by a lot of different pathogenic bacteria. So this can make it more tricky to diagnose and to treat as well. It's very often biofilm associated, which means that you will most likely see metabolic inactivity of the bacteria present. And on top of the biofilm aspects, there's a poor blood flow to the bone, which means that antibiotics and immune cells will not be recruited and transported as easily. So to treat these types of infections, it often requires a prolonged and very aggressive antibiotic treatment. And on top of that, if it was not bad enough already, there's a high rate of recurrence for this type of infection. So you don't get rid of it that easily. The current way to diagnose these types of infection rely heavily on culture-based methods, as is the standard for detecting infections and doing antimicrobial susceptibility testing. Of course, there are other methods that you could complement this with, but this is the most widely used method. And if you look to the right, try to create like a timeline of the ideal scenario from when you obtain the patient biopsy and you do the culturing. If it's a fast-growing bacteria, then you'll have a culture result the day after. You can species identify it by multituf. You can do your susceptibility testing. And on the third day, you will probably have a response on the antibiotics. And then you can start a more or less targeted treatment towards what you find. So this is the ideal scenario. But there are some problems with this technique because in up to 30% of cases, we see that you get a false negative culture result. This can be due to many different factors. It can be due to antibiotic treatment prior to sampling from the patient. It can be due to metabolic inactivity, or it can be due to bacteria that are just very difficult to grow in a lab setting. So what I want to try to do is speed up this process of diagnosing the infection and also the susceptibility testing. With this updated timeline. So ideally, you could get the biopsy and on the same day, with the microcalorimetry, you could detect if there is any bacteria present. And at the same time, you could do susceptibility testing. And then on day 2, start a more targeted treatment. So of course, with this traditional culture-based timeline and methods that are used today, there are a few consequences or results of that method. Yes. So very often the patient will be given empiric broad-spectrum antibiotic just as a precaution, but this can have consequences for the patient in terms of gut microbiota disruption, and also this can drive resistance development in the bacteria. And if this empiric treatment does not cover the actual bacteria from the infection can progress and it will result in a worse outcome for the patient. And of course, this also results in longer hospitalization times and increased costs for the healthcare systems. And if the empiric treatment is not effective, there's an increased risk of recurrence of the infection as well. So as this picture illustrates, we really need to aim for faster detection and a faster way to initiate a targeted antibiotic treatment. And as I have mentioned, we are trying to do this by using isothermal microcalorimetry, which has a lot of pros, but of course also some cons that you should be aware of when using this method. So some of the highlights are that it's label-free and non-destructive, so you don't have to do a lot of modifications to your sample before analyzing it. And also you essentially culture the bacteria in the system while doing your analysis, so you can do downstream analysis on the bacteria afterwards to complement the microcalorimetry. And you can basically use any kind of sample type that you want. In principle, you could dump in the whole biopsy from the patient and see what that gives you of results. And then you have real-time measurement. So you don't have to wait necessarily 24 hours, 18 hours, or 48 hours until you have a reasonable result that you can use. So as I mentioned, it is still basically culture-based since you grow your bacteria inside the system. So species that cannot be cultured in the lab can also not be detected in this setup. And of course, you don't get any mechanistic or genetic insights into the resistance patterns of the pathogen. But you also don't necessarily do that with standard plate culturing. And then sometimes you can find it a bit difficult to decipher these heat flow curves that you get, because the signal you get is a combined signal of all processes generating heat within your sample. But that could be a pro and a con in some specific cases. So these are just some pictures of the setup in the lab that I'm using currently. And here's a schematic of the inside of the instrument that I'm using, with the most important part, of course, being this end chamber, which is the measuring chamber, where each of these wells where you can put your samples in have a dedicated thermopile sensor, which then can translate the heat detected into an electrical signal, and you get this beautiful heat flow curve as you can see on the monitor in the top left picture. So I wanted to use this technology to, first of all, detect bacteria fast from these types of infections, but also at the same time perform susceptibility testing. So you could get both measures more or less at the same time. And of course, you need to have some thresholds or ideas about when you say a bacteria is detected or when it is susceptible or when it's not susceptible to an antibiotic. So here's just an example of a Klebsiella from an osteomyelitis infection. And for the purpose of this study, I've chosen to set my detection threshold at 5 microwatts. So of course, when the untreated control in my system reaches this, I say that it's detected. And for the cutoff to say whether or not a bacteria is susceptible to the antibiotic, I've chosen 20% of the untreated control's maximum value. So if the signal from one of the treatments surpasses this threshold, I'm going to say that the bacteria is not susceptible to the treatment. And this is a simple schematic of the setup I've been using. From the hospital, I have sourced clinical isolates from different patients and of different species to use in this antibiotic panel that I have designed. And then I simply run, or I make cultures of these isolates from the biobank, put them in the antibiotic panel and run them in the calScreener, and then interpret all these heat flow curves that I get. And here are some of the results. There's a list of some of the species that I've been using to generate these results. And all isolates used have been from patients and from an osteomyelitis infection. So what this figure shows is that I basically have two starting inoculums, one that is compliant with the UCAST recommendations. I also use Müller-Hinton media as they recommend to use for susceptibility testing. And then I have a low inoculum as well, just to see what happens if you get a sample with very few bacteria in it. So if you follow the green line here, we can see on the x-axis I have the percentage of isolates detected at a certain time point. So already within 4 hours with the UCAST recommendations, I have detected all the isolates that I have tested so far. If I lower the inoculum to around 50 CFU per milliliter, in some cases that is as low as 5 bacterial cells per sample well in the system. We of course get a delay before we start to detect the bacteria, but after that delay, we are starting detection at the same rate as we saw for the UCAST recommended inoculum. And then the blue and the orange are the time it took to susceptibility profile these isolates with all the antibiotics I have used. So as you can see, that is, of course, much slower than just detecting the bacteria, but nonetheless, it's still within 24 hours. So theoretically on day one. And of course, as I said, these isolates were all sourced from the hospital. So we went back into the data to see what susceptibility results did the hospital get for these exact same isolates. And this table just shows some comparison metrics between the microcalorimetric method and the classical culture-based method from the hospital. And as you can see, we have great agreement, and actually for all of the isolates, the susceptibility profiles came out the same between the two methods. So that's a pretty good sign for the further experiments. And of course, based on this graph here, these results were obtained faster than at the hospital using the standard classical methods for diagnosing. Yes. This is just a case example of, as I talked about, I've also been using low inoculums to test how fast can we then detect and susceptibility test. And this is a staph epidermidis isolate. And as you can see, we get a delay in the untreated control and the detection time, but we still see the same susceptibility patterns. So even though we only have 5 cells in this case per treatment well, we get the same susceptibility patterns, still susceptible to all antibiotics except the lower of the two vancomycin concentrations. And actually, this is the case for most of the isolates I have been testing. You can see it looks the same, just postponed in time because you have a lower starting inoculum. And yeah, I would also like you to notice on this slide how each of the different species have kind of unique, you could say, heat flow signatures or metabolic fingerprints, um, which is quite cool to see. And it makes me think that this technology can also be used for identifying what species it is. You just need a lot of data to do that. And also notice how some of the species have unique, distinct features that you can recognize every time you run your experiments, like Pseudomonas produces a lot of heat, almost 300 microwatts at its peak, which none of the others do. And then this Klebsiella isolate has this very characteristic secondary bumps or peaks after the initial peak, and it still retains that characteristic even at a very low inoculum. And just to justify the use of this technology for this purpose, it has been documented in various other infection types like fracture-related infections and urinary tract infections, as well as prosthetic joint infections. So yeah, kind of the aim or the benefits that we're hoping to see in the end when this project is done is that we can obtain a faster diagnosis, which will enable faster targeted treatment of the bacteria that is causing the infection. So we can more quickly maybe switch from the broad spectrum IV antibiotics to targeted tablets or IV antibiotics and help lower the resistance development and yeah, improve the outcome for the patients and save money for the healthcare system by reducing the days hospitalized. And yeah, it's a very hopeful or optimistic outcome, but hopefully we will see that it holds up someday. So I think there's, other than what I have shown you here so far, a lot of other potential benefits with this method, and I think it can show a lot of hidden things that you can't just see with your naked eye from the heat flow thermograms. And I'm gonna talk a bit about some of those things. So this plot is basically just to show that in general, from my observations and my data, gram-negative bacteria, no matter the inoculum size, which on the right side here, are detected and susceptibility tested much faster than the gram-positive bacteria. And also it seems that some of the gram-positive bacteria are more affected by the inoculum size, so they are more sensitive to the inoculum size. And speaking of inoculums, I have done a more complete range of dilutions for some of my isolates. And here's a Staph epidermidis, here's a Staph aureus. And you can see how beautifully these curves are separated the more diluted your samples are. So the idea with this is that if you can kind of create some reference thermograms like these, I'm very confident that they could be used to predict the bacterial load, let's say in an unknown sample, if you know what species it is. And this is another example of the same with an Enterococcus faecalis and a Klebsiella pneumonia. And you can see, especially for the Klebsiella, that the systematic delay you get between each dilution is almost identical. And every single dilution still retains that unique feature I talked about previously after the initial peak. So you would still be able to recognize this as a Klebsiella just by looking at it. Of course, here for the Enterococcus faecalis, at some point, the curves will start to change their shape a little bit, and the peak height will go down. As you can see with the Klebsiella, it systematically goes down all the way. And as we saw here on the previous slide, for the epidermidis and the aureus, If you go down to the most diluted sample, the orange curves, you can see that the peak height is decreased dramatically and the lag phase is much longer. So within a limit, an upper and a lower limit, I think this is it's very feasible that you can estimate the bacterial load of an unknown sample. Yes. So another thing that this has been used for, and this is from a former colleague of mine and former supervisor, Mads Lichtenberg, and I believe Kasper as well. They looked at some Pseudomonas bacteria where they have high cyclic diGMP and low diGMP, and then they culture them as biofilms or planktonic, and both biofilms in alginate beads and in surface biofilms. And what we can see here is that if you have high cyclic diGMP levels, there's a fast and very large energy expenditure, no matter if it's a biofilm or a planktonic. But you can still see differences in the shape and the features of the heat flow curves to distinguish between the state of growth. So it can also be used not just for detecting an activity, but also detecting how are they active when you have detected that activity. And if you start to analyze your data a bit more, this is just a simple PCA analysis to see how the species and the isolates I have used in my project, how they cluster in a two-dimensional space. If we reduce the dimensions a bit, we can see on this PCA plot, I know it's very difficult to see everything at once, but I will try to highlight some things for you here. So you can see that all the gram-negative isolates I have tested actually cluster down here with the higher the EUCAST inoculum, and the gram-positive bacteria cluster here with the EUCAST inoculum. And then on top here, we have kind of like a long string of isolates, which are all from the low inoculum. And then, of course, this is the graveyard cluster. This is where all the susceptible isolates are put, where there was no signal to detect. So basically what this shows is that you can differentiate between species, you can differentiate between inoculums, susceptible, non-susceptible, if you dive a bit deeper into the data, instead of only relying on the thresholds that I said earlier. This is a very good method to kind of get another view of the data as a whole. And actually a bonus info, if you look down here at the gram-negative cluster, you can see that this and this are actually both Klebsiella isolates, but from two different patients. And yet it is able to distinguish between the two of them. And the same here for the two E. coli isolates from two different patients. The gram-positives here are a bit more difficult to distinguish. You can clearly see here in the middle that E. faecalis, Enterococcus faecalis, are sitting closely together, and the Staph epidermidis here more together. But in general, as I talked about, gram-negative bacteria are detected much faster, and that's partly due to that they just produce more heat in this setup than gram-positives do. So with few data points, your gram-positives start to look more like each other if you do an analysis like this, and there's a bigger difference between the gram-negatives. But still, very exciting that you can go down to strain level in some cases within the same species. So this is a bit off the osteomyelitis and bone infection topic, but I thought I would include it as well because I've been using the calScreener for this project as well. But here we are looking at Pseudomonas aeruginosa, and we've been using a wild type and a VISP-F mutant, which is an overproducer of matrix and biofilm. And just to see what is actually, is the biofilm granting protection, or is it the growth state of the bacteria? So we have used tobramycin to target the exponentially growing bacteria, colistin to target potentially slow growing. And for this heat flow thermogram down here, the cultures have been exponentially growing for 2 hours before we started to treat them. And as you can see, looking at the purple and the green heat flow curves, that it doesn't matter if it's the wild type or the mutant that produces a lot of biofilm. They're both very much inhibited by tobramycin treatment, and they don't really care about colistin, which looks more like the untreated control. And as you can see in the microscopy images, it's just to show that the mutant actually forms biofilms within these 2 hours and at a much larger scale than the wild type does. I'm not sure if I would call it biofilms. It's just closely located single cells. Yeah, so it's just kind of a point to think about, a point for discussion. Like when we take a sample from a patient, we remove the bacteria from where they are, we disrupt biofilms and aggregates, and then we plate them out or culture them in liquid media. Like what are we actually measuring? Because if we give them something fresh to grow on, I think we are reactivating them, making them susceptible where they might not be susceptible at their original location inside of the patient. So yeah, is it actually the biofilms or the state of growth that determines, in some cases, if the bacteria is susceptible or not? Of course, when the biofilm matures, I'm sure more protective features are more well defined and able to confer tolerance to antibiotics. But in this case here, the protection is not present just because the biofilm is present. But yeah, this is an ongoing study currently. So it's of course up for discussion if you have any questions for that. And yeah, that was actually what I have planned to show you today. So happy to answer questions or engage in discussions if you have any.
Excellent. Thank you very, very much indeed, Mads. So I know some people had to leave early. If you have any questions for Mads, you can email them or just get in touch. But we will start with the discussion now, and questions have been coming in as you've been talking, thick and fast. And if you have any more questions in the audience, please just type them in the chat or the Q&A. So we have a question here about the cutoff, the 20% cutoff for susceptibility testing. Where does that cutoff come from?
So I've actually been looking a bit through the literature, but without much luck. And then I decided to test the 20% as you asked about, Tom, but I also tested a 10% cutoff. And I found that thinking realistically about it, you don't know what species you have in what wells, and sometimes you can have, like, you saw that Pseudomonas produces a lot of heat, and sometimes you can have a little bit of overflow, at least in the version we have, of this energy, which can cause it to look like there's a peak in an adjacent well when there is actually not. And often I found that those false peaks would reach the 10% cutoff. So I thought better to be more conservative with the cutoff, to be sure that if I say an isolate is not susceptible, that it is actually not susceptible. So it's mostly out of caution, and of course it can change as I learn. But for now, that's what I've gone with.
Cool. And a related question from Tom as well is how do you decide on the antibiotic concentrations for each experiment?
So that was done in collaboration with a very kind doctor from the hospital, from the department where we got these isolates, and he guided me through what to use. And the panel that we have, or that I've designed for this initial part of the study, maybe I can bring it up. here, if you can read the numbers and the letters, uh, was a panel I decided to use because it covers some gram positives and some gram negatives, and it covers some of the species most often found in osteomyelitis infections. But of course, the plan is to make different versions of this antibiotic panel and tailor it more specifically to osteomyelitis infections in general, but also maybe use some of the empiric treatment that they use at the hospital to see whether they should actually use that empiric treatment or not. So it's an ongoing evaluation as well of what antibiotics to use.
Cool.
Yeah.
Some more questions here. So, do you only detect heat when the cells are in exponential phase? So, basically, and the follow-up question there is if cells are growing kind of slow, does the system still perform? And then do you have to make any adjustment to the cutoffs?
So as I uh, tried to say on my last slide, that if you take something that's slow growing out and you disrupt it and you put it in some fresh media, which you would do with broth microdilution susceptibility testing, you will reactivate their growth and you will see these peak shapes of the bacteria. Um, if they are slow growing or more metabolically inactive, you would still get a signal, but um, I would have to adjust the thresholds for those cases as well, because they might not reach the threshold. And from what I have seen, the heat flow, the shape of the curve is not as distinguishable as when it has this whole peak structure. It more flattens out across time. So it's more of a consistent heat output over time instead of this peak signature that we see.
Yeah, I think we see the same thing. I think when you compare slow growers to fast growers, the peak obviously looks less. But what we do see as well is that when you compare slow growers using microcalorimetry to other methods, you see something in microcalorimetry that you don't see in other methods, which is why people are very interested in this for
Yeah,
example, mycobacterium. Like you can actually leave them in there, let them grow, and you start to get signals before you would ever
yeah.
see anything in a broth or on a plate or something like that. So there's definitely
I have
differences, but it's very sensitive. Yeah.
Yeah, I have used microcalorimetry before to look at Cutibacterium acnes
Ah, right.
cultures,
Yeah.
and of course they are very slow growing, and it takes several days before you can even see colonies if you put them on a plate.
Hmm.
But yeah, I actually managed to see a stable signal already after 40 hours, I think it was. So definitely you see something with this method before you see anything on the traditional culture-based methods, for
Hmm.
sure.
Cool. Follow-up question there. So the biofilm tobramycin results are interesting, and the question is, have you performed CFU alongside to confirm that the susceptibility curves correlate at lower survival?
I've done that previously a little bit, actually parallel to this study with some of the same cultures, and I can see that the CFU levels before and after treatment and what you see in the calorimeter uh, actually corresponds very well with the CFU counts pre and post treatment. So if you see an isolate that is susceptible to a given antibiotic, usually I would also see killing when I do see a few counts. Yeah.
Cool. Another question here. Do you see enhanced metabolic output by the WSPF on a longer timeline than the wild type? So, does overproduction of the EPS, is that a cost?
Um, I do see, well, as you can see in this graph, there is no more to see after 24 hours. Both the signals are baselined, and it actually ran over the weekend, and the signal doesn't pick up again after this. But I do see increased metabolic output by the mutant. And I think that has to do with, at least compared to the wild type, and I think it has to do with the production of biofilm and matrix components that is very energetically costly in the beginning. Yeah.
Cool. And another question there, have you tested kind of really old WSPF cultures, like older than 6 years is in the question here? And do you think the tolerance
Okay.
gained from the overproduction can be seen in these cultures?
6 days, yeah.
6 days, not 6 years.
Yeah. No, I was very
I thought
confused.
you were digging back into the freezer then, looking at
Yeah.
a kind of old culture. No,
Uh,
6 days.
no, I have not tested that old cultures. What I did here was just make an overnight culture and then regrow them for 2 hours. And
Hmm.
that regrown culture was then used for the experiments. So I have never tried to do that with the VESP-F mutant. Mm, but I think, as I also mentioned before, that if it is a very old culture and the biofilm has been allowed to establish for significantly longer than 2 hours, I think I would see less of an effect of tobramycin. Not only because it would probably not be exponentially growing anymore, but also because the biofilm has developed. And the reasoning for doing it this way with only 2 hours of regrowing the cultures to an exponential phase was just to show that the growth phase is maybe in some cases also very relevant to the choice of antibiotic and not just uh, if it's a biofilm or not.
Cool. I have a question. I think it was super interesting when you showed, like the whole premise of the talk is about making better decisions in the clinic and kind of really moving away from broad spectrum antibiotics as soon as possible when you have the data that you need to use a different treatment. And
Yeah.
obviously the timings are much less, and so you can make decisions early. But I was just wondering, based on what you see, like you showed results of kind of, I think it was like gram negatives are detected, and you can do the AST sooner. And you also showed this graph where you show the percentage of isolates that you could correctly AST. So I was wondering if before you reach 100% there, if you say did 50%, that kind of gives you information. It kind of narrows down, the amount of data points you need for the top half. So I was wondering, like, even sooner, like maybe halfway through, well, we've detected all of the gram negatives, so we know that, it must be gram positive if it's up at this level. So you can even start kind of making slightly broader decisions, maybe not the exact antibiotic you need, but you could say, okay, we know it's a gram negative now, so then we'll treat it differently. Or we know it's in this cluster, so we would treat it with these instead. Do you have any idea of, how that could be used practically?
Yeah, of course, I'm not a doctor in the clinic treating the patients, but I definitely think, as you say, maybe you don't need to wait until 100%, or you could pick out some variables, or maybe look, as you say, at the 50% mark here, like how sure can we be at this point, and then narrow in the treatment a bit more. And then as time goes, keep narrowing the treatment more and more. But of course, I think you have to be really careful with this as well, because for now at least, we just need more studies on it and more data on it. But it's very important that the patients are treated in the most proper way to begin with. And I'm not sure what would be accepted in the clinic, how sure you need it to be that this antibiotic is effective. But definitely, yeah. Like looking at the clustering, for example, is it more likely to be a gram positive or negative? Already, if you have the gram positive and negative distinction, you could make a more informed choice on what antibiotics to use. So if you have, let's say, two empiric antibiotics, one targets positives, one targets negatives, you could confidently cut away the one that targets gram negative bacteria and minimize the use of the broad spectrum, and already then you are more targeted to the pathogen that you're looking for.
Hmm. Cool. It's super interesting. It's always nice to ask this question with someone who's like into the data because although yeah, you're not in the clinic, you kind of see things. And I think the kind of traces, while they are complex, when you stare at them all day, you start getting a sense of things of the data that we kind of,
Yeah.
we want to kind of formalize and kind of use in models and stuff, but you kind of see things, and it's really interesting to hear what you think about stuff like that.
Yeah, I definitely think that when we see the, the heat flow like this, we see it live on the screen as we're measuring next to the instrument. And that is, of course, the main output. But I think it's really important to look beyond the heat flow curves as well and try to analyze and see what this data hides.
Hmm.
Because essentially what you get is a time column and then data columns for all your samples.
Hmm.
And just by like looking at the area under the curve or the peak heat or the metabolic rate, like you could take out a lot of variables from this data and use it to do some more data analysis and gain
Yeah.
deeper insights into what you see.
Yeah. It's a very rich it's very rich data. And
Yeah.
then a follow up on that then, how much of this do you need for the PCA? Because that's obviously really interesting how things are separating out. But then do you need to go like you've got 24 hours here. Do you need to use the whole lot or do you use less? And do you think you could reduce it even more so you could actually get some kind of PCA result at a very, very kind of early time point? Because obviously you don't have all the peaks necessarily, but I'm just wondering how
Yeah.
much you need.
Yeah, I have not experimented with that. The one I showed you, I have just streamlined the data, so I'm sure I'm looking at the same time frame for all isolates,
Hmm.
and that was 24 hours,
Hmm.
where I've just been using all of the data,
Yeah.
so it accounts for all of the features. Um, but definitely you could go lower. Like you don't have to look at the 24 hours, and especially if you have a lot more data than what I had available when doing this, you could go even lower, I'm sure, to cover
Yeah.
all potential variants that could arise between these isolates. But I also think you could do or accomplish the same thing by picking out the variables that we talked about just
Yeah.
before this question, and then making a data frame with those variables instead of using the whole data set to
Yeah.
do these clusterings.
Because in this sense, those variables we talked about, essentially, you could pick them in under 12 hours, couldn't you? I guess so you've got the peaks, the area under the curve. I guess the
Yeah,
12 hours plus would not contribute very much variation, or at least you could hypothesize that. Yeah, so it's super
yeah,
interesting the
but
analysis that you're doing. Yeah.
actually, absolutely right. As you can see, most of them are done with all, if you could say, the essential stuff they're doing
Mm.
within 20 or 15 hours for
Mm.
most of them, uh, even at a low inoculum. So definitely, yeah, as long as you streamline the data so you know that you're looking at the area under the curve and it's up until the same time point for all your data.
Yeah. 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 All right. Well, I don't think we have any more questions. If there's any final questions to come in for Mads, please pop them in the chat or the Q&A. And of course, feel free to email us and ask any follow-ups or what have you. It'd be really great to hear how you would like to apply this to your work. But if there's no questions come in, all that remains for me to do is to thank everybody for coming to this webinar. It's been great. We appreciate having you on. Mads, it's been an absolute pleasure. Thank you very, very much for showing us your work and for diving into all this data. It's just fascinating. I think you can see with the questions and myself that we just really love nerding out about real data that comes in from real experiments, and we look forward to see how this goes. So thank you very much indeed.
Thank you for having me.